Hi, everyone. Thank you for coming to my talk. My name is Yuki Chen. I'm a security researcher at Cyber Kunlun, which is a startup security company in China. I have explored multiple targets at Pontoon and Tianfu and I've also been the first place on MSRC most valuable security researchers for 4 years. I also won 2 Pony Awards for Best RC and Epic Achievement. I have found some bugs in different vendors' products, including Microsoft, Google, Apple, Adobe. This session is a walkthrough of our research project on Windows Remote Access Service. We will go through different Windows RS components, analyze their pre-auth attack surfaces, and share some bugs we found. We will also share our thoughts and approaches when doing the research. We will not talk about the exploit details of these bugs today. If you are interested in bugs in Windows Remote Protocols or in Windows Bug Bounty, welcome to join this session. Here's our agenda today. First, we will have a brief background introduction, then we will go through each Windows RS component. Finally, we will have a summary. Now let's start. So why we decided to research Windows RS? In April last year, we read a blog shared by security researcher Alex Nichols, which described a remote null-point denial of service bug in Windows PPTP server. This bug seems very interesting to us because of several reasons. First, we have never seen a Windows PPTP bug before, which seems it is blue ocean. And the second, the bug seems very simple, which means the related code quality is not so good. And next, also most important, this bug is pre-auth and no user interaction, which means this may be eligible for the attack scenario awards in Windows WIP bounty program. If you are interested in bug bounty program but never tried WIP bounty, here is an introduction. WIP bounty is one of Microsoft's bug bounty programs. It awards for bugs that can be triggered in Windows Insider Preview build. There are 2 types of awards, general awards and the attack scenario awards. The attack scenario awards is much more interesting. It awards bugs for particular scenarios, currently only for pre-auth remote bugs and sandbox escaping bugs. It pays much higher than normal bugs. The max payout is 100,000 for a single pre-auth RCE bug. Very nice payment. So if you are interested in the attack scenario awards and want to have a try yourself, before you study, we suggest you to read the bounty rules carefully, check the up-to-date out-of-scope list, and fully understand the attack scenarios. For example, for the below scenarios, do you think they're in scope? Let's see. First, web browser. No, because it requires user interaction. Office document. No, for same reason. The domain user to DC. No, because domain user requires authentication. And the non-default configuration, it depends, which is the most tricky type. So where to find the pre-auth targets? An important way is to learn from other researchers. And you can also explore Windows features one by one with patience. For example, you can check the feature list in a Windows server. Finally, a good temper is a very important one doing bug bounty program. Always remember that the vendor can reject a bug bounty at any stage with no reason. If you insist to have a reason, there's no problem. They can just make up a reason for you. So it's very tough, right? As tough as our life. Yeah. Now let's start exploring Windows RS. Windows RES provides remote access to clients. It contains multiple kernel drivers and user mode services. First, let's look at PPTP. PPTP is an old VPN protocol. It uses two channels, a control channel using TCP port 1723 and a data channel using the GRE protocol. Here's a typical PPTP session. The client sends a start control connection request to establish the control channel, and then it sends a new call request to create a new call. After that, the client sends GRE packets to the data channel, and the GRE packets carry PPP protocol, and the PPP protocol carries other protocols like LCP, NCP, and authentication protocols like DAP, CHAP, and so on. Let's analyze the pre-auth attack surface in PPTP. The first is the kernel driver. It contains code for the control channel. It's pre-auth. The second is the user mode PPP engine. It contains multiple protocols, and all pre-auth part of these protocols are pre-auth attack surfaces. And finally, also previously, all authentication protocols are pre-auth attack surfaces. So let's look at the kernel driver first. The kernel driver registers two callbacks, one for the control channel and one for the data channel. There are some important data structures in the driver. The first is a control structure. It represents a control channel. The second is a call structure, which represents a PPTP call. And next is NDIS VC handle. PPTP driver uses NDIS framework for call management. So each PPTP call contains an NDIS handle. Here's the relationship between them. You can see the client connects to the server by TCP port, and a control object will be created. And then the client can create multiple core objects under a same control object, and they are linked in a linked list. And also each core object contains an NDIS handle here. So where to look for bugs in the driver? First, we can try packet and message parsing and handling, and the PPP state machine. And the second, we noticed the objects have complex cross-references between each other, and they can be accessed from both the kernel and the user mode by multiple threads at the same time. For such design, we'd also like to try user-to-free and the risk condition. Risk conditions are tough bugs to developers. They occur when multiple processes or threads attempt to access the same resource at the same time. I used to be a developer for years, so I understand how difficult it is to write thread-safe code using C and C++. This is because I also messed things up. So we started with a simple fuzzer. This fuzzer uses multiple threads, and it just randomly sends PPTP message to the server. It's quite simple, so we didn't expect too much. However, the fuzzer found multiple crashes with UAF and null-point dereference. All of them are pre-auth. So next, I switched to manual auditing and find more bugs. We didn't choose to rely on the fuzzer because we want to find most of the bugs as soon as possible. This is because the original PPTP bug is published, and our prediction is that we will have more and more competitors soon. So speed is very important for this project. Let's see some examples. This is a core user of the free. The client sends a disconnect request to the control channel, and the function CTLP engine accesses the core object. The problem is that when accessing the core object, there is no log protection, no reference counter protection. So another thread can just free this core object by closing the connection, resulting UAF. Next is a control object reserved free. In the disconnect callback function, the function accesses a control object without any protection. So if another thread sends a stop control request to the control channel, the control object will be freed, resulting UAF. Next is an NDIS VC handle reserved free. The client sends a new call request to the server, and the server will create a new NDIS handle. Then it accesses a handle without any protection. So another thread can free this NDIS handle by closing connection. This one is a little bit more complicated. It's a recognition between the data channel and the control channel. The first thread sends a GIE packet to the control data channel, and the callback function will access a call object without lock or reference counter protection. So if another thread closes control channel, the call object will be freed, resulting in UAF. Next, let's analyze user mode service pre-auth attack surfaces, including the PPP engine and authentication protocols. We will see examples for them. For PPP, we will use LCP as an example. LCP is used to configure parameters and later protocols in PPP. It's a pre-auth protocol. This is a heap buffer or read-write vulnerability in LCP server. It occurs when the server handles a malformed LCP malformed configure request. A LCP configure request contains multiple LCP options. As defined in the upper right here, you can see the minimal size of a LCP option is 2 bytes. And the vulnerable code just simply copies all LCP options in the input packet to the destination buffer. So where is the problem here? The problem is that when copies the option, it does not correctly validate the length field of the option. So if the length field is less than the minimum size of a LCP option, for example, if it is 1, then the memory copy here will only copy 1 byte to the destination option. Then in such case, the length field of the destination option will be uninitialized. And this uninitialized length will be used here to advance the destination option to next position, which can go beyond the end of the destination buffer, resulting OOB read and write. Next, let's analyze authentication protocols. Windows RS supports multiple authentication protocols, which can be negotiated between the client and the server. By default, EAP protocol is used for built-in Windows VPN types. It supports username, password, Windows logon credential, or certificates, or other methods. We will not go through each authentication protocol here. Instead, we will use PEAP as an example. PEAP is protected EAP. It supports TLS and is more secure. It's implemented in EAP TLS. This is a heap buffer flow write bug in PEAP fragmentation feature. PEAP supports packet fragmentation. And each time when a new fragment packet comes, the function stores the next fragment will append the packet data to a fixed size buffer here. And the root cause is that there's simply just no boundary check when appending the data. Very cool. So whenever you see a protocol that supports fragmentation feature, make sure you will check the implementation carefully. This is because there are many bugs in fragmentation feature in the past. Besides Windows authentication, Windows RAS also supports radius authentication. Microsoft's implementation of the radius protocol is called Network Policy Server, or NPS for short. It uses UDP ports and is implemented in ISI detail. Here's the example. It's a pre-auth information leak bug in Windows Radio Server. The server tries to read a 16-byte signature from the signature attribute in the packet without validating the length of the attribute. So if the attribute length is 0, it will read out of bounds. This is a pre-auth DOS bug in Radio's proxy server. The loop here simply calculates the count of the attributes in the input packet. Can you see where the bug is? It's simple. If the length field of the attribute is 0, then this loop becomes a dead loop and will never exit. While do bug hunting, we tend to focus on RCE bugs, but ignore the less severe bug types, like denial of service or information leak. But when you play with Windows Bounty, the pre-auth remote DOS or information leak bugs are also very high cost performance, and you shouldn't miss them. Just image 30,000 for a single pre-auth denial of service bug. Okay. So before we finished our PPTP research, we started to have collisions with other researchers. We are lucky that we started earlier, so most of the time our bug was the first, even when bug collision happened. So our experience is that you don't often find such high cost performance targets in your bug hunting career, so they are very precious. Make sure you catch the chance when such targets comes. Okay. So the result of our PPTP bug hunting, we find many pre-auth RC bugs. Most of them are risk condition bugs, and now we have enough motivation and confidence for the next Windows RS protocol, which is SSTP. SSTP transfers the PPP traffic over HTTPS. It is invented by Microsoft. It's also used in a 0.2 site VPN. Like PPTP, SSTP server also contains both kernel driver and the user mode service. SSTP packet first reaches the user mode service, SSTP svcdel, and then is dispatched to the kernel driver, ras_sstp.sys. Let's analyze the pre-auth attack surfaces in SSTP. The first attack surface is the kernel driver. It handles SSTP packets and maintains the life cycle of a SSTP core. The next attack surface is the user mode service. It maintains communication over HTTPS between the client and the server. So let's check the kernel driver first. It handles SSTP messages. There are two types of SSTP packets, the data packets and the control packets. They are functionally similar to the PPP data packets and the control packets. The most important data structure in the driver is SSTP context. It represents a SSTP core session. And also the same, it uses NDIS framework for core management. So where to look for bugs? But first, we can try the SSTP packet parsing and message handling and the SSTP state machine. And the second, because the SSTP server has many similar designs with the PPTP server, so we also want to try user-free and the risk condition. So we developed the most simple but fuzzer we have ever developed. It just simply send a connect packet to the server and sleep for some time and then close the connection. It uses multiple threads. We also bought a lottery ticket before starting the fuzzer because the fuzzer is too simple. Yeah. So when do bug counting, sometimes we will make some negative assumptions, such as further is too simple, no way to find the real bugs, or such simple type of bug shouldn't exist in this material product. Our experience is that we should avoid such assumption before we actually looked into the details. As an example, our super simple fuzzer found crashes, which seems exploitable. And by the way, I didn't win the lottery. Next, I improved the SSTP fuzzer, meanwhile switched to manual reverse engineering and find some more bugs. Let's see some of them. This is a SSTP context user free. This code pattern is very common in SSTP driver. It retrieves a SSTP context by handle and then add a reference counter to it to avoid UAF. However, the problem is that when adding the reference counter, there is no log protection, so another thread can free this SSTP context before the reference counter is successfully added. Okay, next, this is a NDIS handle user free. We have seen similar bugs in PPTP server, and the root cause is also the same. No log protection when accessing an NDIS handle, so another thread can free this handle at the same time. This one is interesting because it does not happen in the SSTP driver itself. Instead, it exists in the NDIS1 driver. NDIS1 processes PPP packets, and for each packet, it will create a receive description structure which contains a NDIS handle for current core. These receive descriptions are inserted into a list waiting for the user service for receiving and processing. The user mode service calls IO receive packet to receive a packet. It simply pops a receive description and then copies the packet data to user mode buffer, then frees the receive description structure. The problem is that when frees the receive description structure, there's no log protection, so another thread can free the NDIS handle inside it at the same time, resulting in UAF. Next, let's check the user mode. This one is signed by our fuzzer, by our super simple fuzzer. The root cause is that lack of multi-thread protection on a global timer array. Next, let's analyze the user mode service. It's relatively simple compared to kernel drivers, so actually not too much to analyze. But anyway, let's still give it a try. This is a risk condition UAF triggered by worker thread. For each packet from the client, the service will create a received buffer structure and link it to a list. The packets will not be processed by the main thread. Instead, a worker thread is responsible for processing these packets. This design is common in Windows Server program. The worker thread simply processes the received buffer one by one. The problem here is that if another thread closes the session at the same time, and there are still received buffers in the list, then all received buffers will be freed together without any protection. Even some of the received buffers are still being accessed by the worker thread, resulting in the user free. So when looking for risk condition bugs in Windows, our suggestion is that we can focus on important resources. You can draw a picture of the life cycle of the resource, like where it is created, where it is used, and where it is deleted, and check the conditions for each access. For example, is there any spin lock protection, or is there any reference counter protection? after the access happens in a callback or worker thread, what dispatch level it is when accessing the resource. And after that, you can try to find the risk conditions between different access points. So the results of our SSTP bug hunting is quite good. We find a lot of bugs, and the risk condition rocks again, and we are already prepared for the next Windows RAS protocol, which is L2TP. L2TP relies on an IPsec tunnel to be established first, and it uses a UDP port. The LTP packets are sent through the IPsec tunnel to the kernel driver RASL2p.sys. Let's analyze the pre-auth attack surfaces in L2TP. In L2TP, there are two authentications. The first is one establishing the IPsec tunnel. It's a partial authentication, and a pre-shared key is often used in this authentication. And the second authentication is a full authentication to fully authenticate the VPN user. So when talking about restricted pre-auth attack surfaces, then the only pre-auth attack surface in L2TP is IPsec, including the IK protocol, which we will discuss later. However, since a pre-shared key is often shared among a large group of users, so it is not considered as a strong secret. So it is also useful if we can find bugs after the partial authentication and before the full authentication. In such case, the kernel driver RASL2TP is also the attack surface. Now let's analyze the kernel driver by starting by introducing two important data structures in the driver. The first is a tunnel object. It represents a L2TP tunnel. It's similar to a PPTP control structure. And the next is a VCCB, which represents a L2TP core. It's similar to a core object in PPTP. The entry point of L2TP packets in the kernel is L2TP receive. It processes two types of L2TP messages, control message and data message. So where to look for bugs in the driver? First, we can try message parsing and handling, including the L2TP state machine. And the second, based on previous experience, we'd also like to try UAF and the risk condition. As usual, we'll develop a simple fuzzer for starting. It uses multiple threads, and it mutates L2TP messages based on coverage, and it sends messages randomly to the server. While fuzzing L2TP kernel driver, there is a useful tip shared by Alex Nichols. You can disable the IPsec by modifying the registry entry. So our fuzzer got a few crashes, including UAF and the null point dereference. And then we switched to manual reverse engineering and find some other bugs. Let's see some examples. This one is found both by our fuzzer. It's the UAF in control message. Once the server received a control message that is out of sequence, it will make a shallow copy of the message. The problem is that after returned from L2TP receive, the original UDP packet will be freed, while the shallow copied message still contains pointers to the original UDP message, resulting UAF. This is a tunnel UAF caused by timer callback. In the callback function, you can see a tunnel object is accessed without any protection, so another thread can simply free this journal object at the same time. This is a VCCP UAF. The client sends a new call request to the server, and a new VCCP will be created and inserted into the terminal's VCCP list. Then the function accesses the VCCP without any protection. So another thread can close the terminal, which will free all VCCPs in the terminal's VC list, including this one, resulting UAF. Next, it's yet another NDIS handle UAF in yet another protocol. And the root cause is also the same, lack of protection when accessing an NDIS handle. Okay, so if you remember the NDIS UAF we introduced in the SSTP session, now for short, we just find exactly the same bug, this time in L2TP. Very easy bug. So the result of our L2TP bug counting, we find some bugs in L2TP kernel driver, and all bugs are triggered after the IPsec kernel is established. So our last Windows OS protocol to discuss today is IKE. IKE is an authentication protocol to establish security kernel for IPsec. There are two versions of IKE, IKE version 1 and version 2. Windows L2TP server uses version 1, and there is also a built-in VPN type in Windows based on IKE version 2. It uses UDP port and is implemented in IKE ext del. The pre-auth attack surfaces are IKE packet parsing and processing, and also we'd like to try UAF and the race condition. So we start to learn the spec of IKE protocol, and this often happens when we research complex protocols. We just get tired and just want to start fuzzing first. So we developed a mutation-based fuzzer. It fuzzes IKE version 1 and version 2 messages, and it also uses multiple threads to see if we can find any use-after-free or race condition bugs. The fuzzer finds some crashes, mostly are a null point dereference bug, so it seems the result is not so good. So we switch to manual reverse engineering and find some other bugs. Let's see some example. This one is a bug in IKE version 1 fragmentation feature. And if you still remember the PAP fragmentation bug we introduced before, we have said that the fragmentation feature often leads to bugs. And this is yet another example. An IKE packet starts with a ISAKMP header, and in normal code path, the server will check the packet to make sure it contains a valid ISKMP header. However, in the fragmentation path, the reassembled packet just skips the header check, so an invalid ISKMP header can go through to the later code path, which can cause various problems. Okay, next, this one is a typical integer overflow bug, which can lead to OOB write. It occurs when the server tries to decrypt an encrypted IKE packet. When computing the size to decrypt, there is an integer overflow here. This is another similar bug, like previous one. It's also an integer flow bug, which can lead to OOB write. It also occurs when the server tries to decrypt IKE packet. Next, this is a pre-auth DOS in IKE version 2, this bug can be triggered by sending an IKE packet with a zero-sized vendor ID payload, which can crash the server. And next, this is yet another NDIS handle used free in IKE v2 VPN. By finding this bug, we unlock the achievement that we have found NDIS handle used free bug in every Windows VPN protocol we researched. Very cool. So the results of our IKE bug hunting, we find Pre-Auth RC and the denial of service bugs in IKE protocol, but not so many bugs, but not as many bugs as other protocols. Especially, we didn't find many risk condition bugs like other protocols. So it seems to us that IKE is more secure than other protocols, so choose IKE version 2 if you must use a Windows VPN. Okay, all good things must come to an end. While we believe there are still many Windows RAS bugs yet to be discovered, Microsoft has changed the bounty rule and added RAS to out-of-scope list for attack scenario alerts. We are already familiar with such bounty rule changes. It just means to us that it's time to find a new target. So, question? Do you know the similarities between a productive bug hunter and a playboy? The answer is say move to next target fast. Yeah. Okay. Last part. So for future work, we believe Windows Pre-Auth bugs are still very high cost performance and a good choice when we select targets. So we will continue to shave up the pre-auth attack surfaces in Windows, and there are pretty much stuff to look like authentication protocols, network protocols, and domain services, and so on. All are waiting for your exploring. Okay, a summary for our session today. We introduced the implementation of Windows RAS VPN protocols, and they are complex with both kernel drivers and user mode services, making them good targets for remote pre-auth bugs. And don't forget to try risk condition when researching Windows remote protocols. Use both fuzzing and manual auditing. Avoid only relying on one method. Be smart, eager, and greedy in bug hunting. And finally, we wish everyone a big success in your own bug hunting journey. That's all for our session today. Thank you again for listening. Should you have any questions, you can find me on Twitter. Thank you again.